So in this section 1.5, we discuss the degree of a vertex. We've come across this idea already in the class before, and essentially the way that we've been describing the degree of a vertex is just how many neighbors it has, right? How many other vertices that it's adjacent to. Except not all graphs are simple graphs, and that definition doesn't necessarily make sense if you're looking at a graph that has multiple edges or loops. So we're going to define degree a little bit more carefully here, and we'll say that the degree, which we denote delta G of V, of some vertex V in a graph G, is the number of edges that are incident with V. In other words, how many edges are coming out of that vertex. And if G does happen to have any loops, remember a loop is just an edge from a vertex to itself, then we're going to count that loop as two different edges, right? Because it sort of looks like there's two different edges coming out of the vertex for that one single edge that's a loop. Okay, now we're going to define delta of G, right? Little delta of G is going to be defined to be the minimum of all the different degrees of the vertices in the graph. So this is just saying if you look at all the degrees of every single vertex over your entire graph, you take the minimum, we'll call that just plain delta of G. And we'll call big delta of G, right, this is a lowercase delta, this is a capital delta. Big delta of G is the largest degree of every vertex in the graph, right, the largest possible degree over all the vertices in the graph. So let's look at an example and make sure we understand this. In this graph here, we can find delta of G of each one of these vertices. Delta G of the vertex A is the degree of A. Okay, there's two edges coming out of it, so this is 2. Similarly, delta G of B, there's 1, 2, 3 edges coming out of it, so this is 3. Delta G of C is going to be the degree of C, 1, 2, 3, 4. Delta G of D, this is where you have to start being careful here, because D actually has only 1, 2, and I guess if you count itself as a neighbor, it has 3 kind of neighbors here, right? 3 vertices that it's adjacent to. But its degree is going to be actually 1, 2, 3, 4, 5, 6, because we count that loop twice, and because there's a double edge here connecting D to E. So we're going to count each of those as 2 separate edges, so it contributes 2 to the degree. So altogether we get a degree of 6 for D. The degree of E would be 1, 2, 3, 4. And finally the degree of F is just plain 1. Right? Now that we've listed all the degrees of all the different vertices of the graph, we can define delta of G. Delta of G is defined to be the smallest of all the degrees of the graph. The smallest degree is 1. Right, degree F has, or vertex F has degree 1. And the largest of all the degrees would be 6. So big delta of G is equal to 6. Right, so this is why we're defining this as the number of edges incident, because we want to make sure that we're accounting for multiple edges and for loops. But if your graph is a simple graph, then this delta function, this degree function, is really just telling you how many neighbors a vertex has, how many other vertices is it adjacent to. And so in a graph of order n, if your graph is a simple graph, if we're not allowing for any loops or multiple edges here, then for every vertex V in your graph, the degree of that vertex can be at most n minus 1. Right? It's less than or equal to n minus 1, because at most you're going to be adjacent to every other vertex in the graph. You're not adjacent to yourself because it's a simple graph, there's no multiple edges, and so your degree is going to be bounded above by n minus 1. And furthermore, it's always going to be bounded below by 0, because you can't have a negative degree. That doesn't make any sense. So this is true for all vertices in the graph, for all V in the vertex of the graph. Okay, but for any finite graph, no matter which one you're looking at, if we wanted to look at the sum of all of the degrees over all the vertices in the graph, in other words, come back up here to this picture here, we have 2, 3, 4, 6, 4, and 1. If we were to add up the degrees of all these vertices, we would get 3, 4, 5, 6, 7, 8, 9, 15, 20. Right, the sum of all the degrees here is 20. Which happens to be, if you go back and count all the edges in the graph, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. happens to be twice as big as the number of the edges in the graph. And in the warm-up problem, we saw a similar thing where if we added up the degrees of all the vertices in the graph, we ended up getting twice the size of the graph, right? We ended up getting 2 times the number of edges. So we can say it's equal to 2 times epsilon, where epsilon is the size of the graph. The number of edges of the graph, right? Size means number of edges. And the proof here is pretty simple. I guess I didn't leave myself space for it, right? But as a very simple proof, we've sort of talked about it already before. When you add up the degrees of all the vertices, you're accounting for every edge exactly twice, right? When you add up, when you say that C has degree 4, you're counting those 4 edges, but you're also going to count each one of those edges again when you count the degree of A, the degree of B, the degree of E, and the degree of D. Okay, so every edge gets counted twice when you sum the degrees over the degrees of all vertices. Every edge gets counted twice, therefore this sum is going to be twice the number of edges. And this gives us a nice corollary, which is that, and this again is something we saw in the warm-up problem, every graph has to have an even number of vertices with odd degree. In other words, in any graph, simple or otherwise, it's impossible to have an odd number of vertices of odd degree. Dog is sneezing, sorry. And so we can use our corollary to prove this. Let's try to think about why this is impossible, just sort of in a very kind of theoretical way, or just sort of thinking through this. If we were to have an odd number of vertices of odd degree, right? Let's say maybe we have some vertices of even degree as well, and we try to connect them up again, right? We have to connect these to each other in some way. If you have an odd number of odd degree vertices, you're going to end up with some edge getting left out, right? So let's try to formalize that with a proof here. And we're going to do that by kind of taking your vertex set V and breaking it up, partitioning it into 2 different sets. The set of vertices with even degree and the set of vertices with odd degree. So we can partition the set of vertices V into 2 sets. Let's call them E and O. So we're going to let E be the vertices from your graph such that the degree of that vertex is even. And we'll let O be the set of vertices in the graph such that the degree of that vertex is odd. Right? Every single vertex in your graph is either going to have even degree or odd degree, and so this will partition the set of vertices into 2 sets here. All right, now we're going to show that the cardinality of this set, right, the cardinality of this set O has to be even. In other words, there's an even number of vertices with odd degree. Okay, so to prove this, we can use theorem 1.5.1, and we know that if we were to sum over the degrees of all the vertices in the graph, we'll get twice the size. We'll get 2 times the number of edges, okay? And so because we can partition these vertices into 2 sets here, we can break this up as, let's say, the vertices in even. So first sum up the degrees of all of the even degree vertices, and then sum up all of the degrees of all of the odd degree vertices. Let's call these W just so that we're not using the same variable twice. And O. Okay, right, we're just saying count the even ones first and then all the odd ones. And we know by theorem 2.5.1 that when you add these all up together, you're going to get twice the number of edges, right? And the number of edges is an integer, which means this is an even number. So this sum has to be even. Well, this sum right here, just this part, is guaranteed to be even because we're adding up a bunch of even numbers, right? These are your the set E is the set of vertices with even degree, so each one of these degrees is even. When you add up a bunch of even numbers, it's even. So since dg of v is even for all vertices in that even set, this sum is even. Okay, and this is going to be a sum of a whole bunch of odd numbers, right? We want to argue that it has to be an even amount of them, right? It has to be an even amount of vertices with odd degree. And so because the whole sum altogether is even, and because this part is even, if this were odd, then we would have a problem, because on the right-hand side of this equation, we'd have an even number here for this sum, and an odd number of odd numbers added together is odd, so an even plus an odd would give me an odd over here, which would be a contradiction, right? That wouldn't work, which means we would need this sum to be even, and that can only occur if we are adding an even amount of odd integers. Which means that the cardinality of this O set of the odd degree vertices must be even. So this is just sort of a nice little number theoretical type counting argument about evens and odds. Okay, our last result for section 1.5 is if we let G be a simple graph of order n, and if we knew that for every pair of vertices u and v that are non-adjacent, right? Non-adjacent means there's not an edge connecting them. If for every pair of vertices u and v that are not adjacent, you have that the degree of u plus the degree of v is greater than or equal to n minus 1, where n is the order of the graph, then we can conclude that that graph G must be connected, and furthermore that the diameter of that graph is less than or equal to 2. Right, so let's parse this. And just to be clear, sometimes we omit this subscript of G if it's sort of clear in the context that we're talking about the degrees of vertices rather than delta of the graph, the smallest degree of the graph. But that's what we mean here. Okay, so what this is saying is that if you have a graph, a simple graph that has the property that for any two pair of vertices that aren't connected by an edge, their degrees added together is at least n minus 1, then you know that the graph is connected, and furthermore, you know that the diameter is less than or equal to 2, which means there has to be a path of length 2 connecting that pair of vertices for every pair of non-adjacent vertices. In other words, for every pair of vertices in the graph, either there is an edge connecting them, either they're adjacent, or there's a path of length 2, right? There's sort of some intermediate vertex that connects them with a path of length 2, or that's adjacent to both of them. Okay, so how do we prove this? Well, there's sort of two things that so let's start off by saying we're trying to prove that G is connected. How do we prove that G is connected? Well, we need to show that for any pair of vertices in the graph, there's a path between them. So I don't want to use u and v because we've already used it up here, so let's let x and y be vertices of the graph. We must show there's a path between them. In particular, we're going to end up showing that that path is of length less than or equal to 2. Now these two vertices that you've chosen, they're either going to be adjacent to each other or they're not. So let's break this up into two cases. X and y are adjacent. In other words, xy is an edge of the graph. If xy is an edge in the graph, okay, there's clearly going to be a path. It's a path of length 1. It's a kind of an obvious path here. It's trivial, almost. So then there is a path xy connecting, well, there's an xy path, namely the path x comma y. And so this is sort of trivially true. So the more interesting case here would be case 2, if x and y are not adjacent to each other, xy is not an edge in the graph, Okay, so if this is the case, then by our assumption up here, we're assuming that the degree of x plus the degree of y has to be greater than or equal to n minus 1, right? That's our assumption here. For any two non-adjacent vertices, in this case x and y are non-adjacent, then the sum of their degrees is greater than or equal to n minus 1. So we have delta g of x plus delta g of y is greater than or equal to n minus 1. Okay, now this is a simple graph, so there's no loops and no multi-edges, and this is a graph of order n, which means x and y are already accounted for, and so there's n minus 2 other vertices in the graph. There are only n minus 2 other vertices in the graph. And if we look at all the neighbors of x and all the neighbors of y, we are counting n minus 1 total vertices, which means by the pigeonhole principle, they have to have a repeat here, right? If the degree of x plus the degree of y is greater than or equal to 8, but there's only 7 other vertices in the graph, well, then they're going to have to share a neighbor, right? There's not enough vertices for them to not have a neighbor in common. And so there must be some vertex W in the vertex out of the graph such that x is adjacent to W and y is adjacent to W. In other words, they have a common neighbor. So xW is in the edge set and YW is in the edge set. Okay, so what does that mean? Well, essentially, you've got x connected to W, which is then connected to y, and there you have your path of length 2. So we have the xy path, xwy of length 2. And we just chose these original vertices x and y arbitrarily, and we've shown that either they're adjacent to each other, in which case there's a path of length 1, or they're not adjacent, in which case there's a path of length 2, which means the longest possible, shortest path in your graph would be of length 2. So the diameter is, so G is connected, and the diameter of your graph is less than or equal to 2, which proves this theorem 1.5.2. Now we also have the following corollary, which says if G is a graph of order n, and if delta of G, remember that's the smallest possible degree over all the vertices, is at least n minus 1 over 2, then we can conclude that G is connected. And I'll leave that for you to try as an exercise. We'll go over it in class in case you're stuck.